Hello everybody, my name is Marc. I'm full professor at Université de Bretagne Sud in Lorient, France, and I'm happy to present today the Julia language that I found suitable for operation research. First, I would like to thank my colleagues, Dr. Alexandre Olteanu and my two PhD students, Quentin Perrachon and Erwan Tullier, for improving this presentation. First, if you want to know more about me, you can just Google my name and you will see what I'm doing in research. Basically, I'm using quite a lot of tools coming from the operation research community, heuristics, meta-heuristics, mathematical programming, and mathematics. And I get a main goal in my research is to design efficient solving methods for solving combinatorial optimization problems. And I got a recent interest in combining meta-heuristic and machine learning, and a more recent interest in quantum operation research, where I try to use quantum computers to solve large-scale optimization problems. And I get quite a wide range of different applications, working on routing and scheduling problems, wireless sensor networks, sonar networks, warehouse management, or any kind of combinatorial optimization problem. I'm also using a lot of programming for my class, and I'm teaching in different programs in mathematical engineering, electronic design, production management, industrial engineering, and I'm teaching different courses and mainly centers around operation research with introduction to operation research and graph theory, mathematical programming, heuristic and meta-heuristics, something closer to computer science like data analysis and data management, including a bit of statistics, and large-scale optimization. And the type of students that I have are coming from the last year of bachelor degree to master students or engineer students. And the type of students I have are, of course, classical students, but I have also a master program in full distance learning in mathematical engineering. So we don't see the students physically, we just teach from distance. And we have also professional students. So if you understand well, I'm not a specialist in computer science, but I use computer programming languages in every class. And this is very important for the rest. If you reach my age, probably you have learned quite a number of different languages or went through. I try here to sketch the different languages I've been through, not including the scripting languages, but you see that I've been through Pascal, Ada, C, C++, and Python and Julia. And now I'm well aware of how Julia works and how I can use it for research as well as for teaching. Then I'm really a fan of this language. And by the way, just to give you a flavor of how I've made this figure, then I use these 3 lines of Julia language. Very easy to draw this figure. So let's start. Why Julia? And I want to give you 5 reasons to learn Julia today. First, the speed. So Julia is as general as Python, as statistics friendly as R, but as fast as C. And this is very important for most of us when we design optimization methods, so solving methods. The syntax also is dynamically typed, closer to R and Python, and very easy to learn. And you will understand each piece of code that I will show you very easily. I like also this memory management, which is completely automatic, so you don't have to worry about pointers and free memory or whatever. You just rely on Julia ability of this memory management. Multiple dispatch is also an important feature, is the ability of the function to behave differently based on the different type of arguments. And this is very important, especially for the speed of the Julia language. And my last reason, and I find that this language is very operation research friendly, well adapted to OR, especially with rapid prototyping, speed, of course, we mentioned it already, and the various packages that you can find around, and the link to other languages. You have a library in a different language, you can still use it, and that's very important to me. Let's start. That's the main entry point. I'm going to switch to HIT. So that's the web page of Julia, and the first step for Julia is to download it. So you go to the download page, and here you can still see that you have the latest release in every platform. And so Windows, of course, Macintosh, Linux, different architectures. And if you want to play, you even have the source code, okay? So on this web page, I can just remind that Julia is fast, dynamic, reproducible, composable, general, open source. Very easy to learn here and to start with. You have also access to the documentation, which is a very nice feature. And for example, if you search for the mean function, I can enlarge the screen a bit here. You see that this mean function belongs to the package statistics. And if you click on it, then you have a description of the mean function, and of course also an example. So using statistics, you call the package, and here you call the mean function over the numbers from 1 to 20, and you get, of course, 10.5. Another important part here is the Learn tab. If you want to learn Julia, and this is probably what you need to do, so you have the Julia Academy, where you have the best instructors on video for teaching you Julia. You have this Exercism Julia track, where you can learn step-by-step Julia language and come to the next level once you finish complete a previous one. You have a YouTube channel, of course, that's very on fashion now. And moreover, you have like tutorials on different parts of Julia. And if you want to know how to learn Julia for data science, for example, then you have this here entry point, or any specific topic that you want to get to know. Okay. So let's come back to the slides. Where are my slides here? So let's get into it. The first part, once you have installed Julia, is to start the REPL. REPL means read, evaluate, print, loop. And this is the main place of Julia. So let's go into it. I'm here in my terminal. I just type Julia, and you get Julia immediately ready for it. And you can start playing with Julia here. So for example, we already have seen that there is a package called statistics, better like this. I can regenerate a random vector of numbers between 0 and 1000 excluded, of size 10, for example, here. So I get my vector, and I can calculate the mean of my vector just by calling this function. So you see that it's very quick, very fast, and you can use it immediately. So you don't need any program for calculator, for example. You already have everything here. What is interesting is that this is not the only way of using Julia. You can use one of the editor. Here I use VS Code, and you have this piece of code which is very close to what we have seen here. So using statistics, you declare the random vector, and then you print the vector, print the mean value. You just play here. VS Code start the REPL here in the bottom, and then execute your piece of code. So that's very interesting because here you have a complete editor, but you still have access here to the REPL. So you can just enter a command of the REPL to see what's going on. And you have your code here running, so you can modify your code. If you come back to the REPL, you can, of course, call the files that you have created. So with the command include, you just include the command here, and then it executes the source code you have. So it generates this random vector, calculate the mean of it. Another way of doing this, you can just quit the Julia REPL, and then you can call your source file just by typing Julia and the name of the source files, and you can re-execute this several times. Okay, so it's very transparent for you. Let's go back here, so it works. And the last way of using it is to use Jupyter with notebooks. So let's go into it. I have here my Jupyter notebook open with this test min function. So you can just play, just press here Shift Enter and then execute line by line. You can put everything in one line. So I just generate here 100 vector, and then I calculate the mean of this vector. So you see we have different ways of playing with Julia code. I'm coming back to the REPL because this is the place I like most, and I would like to show a few tricks on this REPL. For example, you can enter shell commands by pressing semicolon, and that's very interesting because you can, for example, list the files in your folders. So that's important, but you can also run extra programs here and get the output of this program into your Julia REPL. You get out of the shell command by pressing the backspace, and you can also access the help just by pressing a question mark. Here, press a question mark, and then I type if, and then I have the syntax of the if statement. Okay, so you see that you have everything usable here. You want to remember how works the mean function, then you have here the example of the mean function. So you see that's very easy to play. Another important feature is that Julia is close to mathematical language. So for example, you have your A vector, you want to transpose, you just type A quote or A transpose, and then you have the transpose vector. So you see that that's very close to what we do in mathematics. And the last feature I want to show you here in this REPL is that this REPL uses Unicode's formulation. So if you use the \lambda symbol, press tab, then you get lambda, and you can use this lambda symbol as a variable for your program. Okay, so then you can use lambda times A, and then you get the vector A multiplied by this constant lambda. And everything that is sound mathematically is doable in this REPL or in Julia language in general. I'm going also to show you something that is very nice. If you generate a random matrix, let's say between -1 and 3 of size 3 times 3, with the linear algebra package, you already have access to what you need in linear algebra here, the determinant, for example. Okay, so that's very important and very attractive for using this language, Julia language. Let's come back to the slides. We talk about the REPL. I already mentioned that Julia is fast. And just to make the short story, if you call a function, Julia will specialize that call all the way down to its concrete type, thanks to multiple dispatch. And in the backstage, you have this low-level virtual machine and just-in-time compiler that works and makes your code very efficient. We already mentioned that Julia is as fast as some other language and mainly C. So we should go into it and see if it's true. So let's move back to here. So I borrowed this notebook from the authors of the Julia language. The notebook is just very simple. You define the sum function, and we've made different implementation of the sum function. So C unwritten, of course, C unwritten with the fastmath compilation option. Python built-in, Python with NumPy, Python unwritten, Julia built-in, Julia unwritten with multiple dispatch, so single instruction, multiple dispatch, to improve this. Okay, and then we have a summary of benchmark. I'm not going into detail of everything, but just to be sure that everybody understands how we are calling a function called sum of A. A is a vector, and we make the sum of I equal 1 to n of AI. Sorry. So we generate 10 million random numbers, put this in a vector A. So the random numbers are uniformly generated between 0 and 1 excluded. And we make the sum, so we obtain something close to 5 million. Okay. So how are we going to make the benchmarking? First, we can use the macro time. So at time of the call of sum of A tells you how much time it takes and how much memory it takes for this. But if you want to make stronger benchmarks, then you need to use the benchmark tool package. So you just call this benchmark tool here using benchmark tools. And then you can write the different codes. So a very interesting feature here, you see that we can write native C code inside Julia. Okay, so you need to learn more about it and how it works, but basically with a bit of help, then you are able to write down this code. And this is the sum function that you can write here for summing this big vector. And these are the lines for compilation, so classical compilation. And then we have the C-sum function coming out of this. And you make, of course, the sum. You get the 5 million something here. And you can just check if the C-sum function is equivalent to the sum that we get before. Approximately equivalent here, because then, of course, numerical instabilities. And then you can do the benchmarking. So you call the benchmark function of this, and then you get the output. And what does it say? You need here on average 11 milliseconds to run this C-sum function. Okay. Then we put everything in a dictionary, and then we are going to compare at the end. So now, second piece of code is the C with fastmath option. So that's the same source code as before, but you just add here the fastmath option for compilation. So that's very classical here, and you put the result in the dictionary. Now we are going to compare with Python. So you have the built-in sum of Python. So you just call the package pcall, and then you call the sum function, you execute it, and you put the results of the benchmark into the dictionary. You can do the same with NumPy. So NumPy is known for improving some of the function, and of course it takes advantage of the hardware with single instruction, multiple dispatch as well. So that's the way we call here this function, and we put the result into the dictionary. And the last way of comparing with Python is the unwritten. So here you define just a piece of Python code. and this is very classical, and you put the result in it. And now we compare with Julia built-in, so that's the sum function inside Julia. With Julia unwritten, you see that this piece of code is very similar to the Python here, and the same unwritten, but with the single instruction multiple dispatch macro for improving the resolution. So the summary is here, and in that summary you can see three different groups of results. So you see that C with the fastmath option, Python with NumPy, Julia unwritten with SIMD, and Julia built-in. The four of them run into the same time frame, less than 8 milliseconds. Then you have C and Julia unwritten, 10 milliseconds. So you see, even if you do something in Julia that could be done better by Julia built-in or other strategy, and it still run quite fast enough, okay? And then if you want to compare to Python built-in and Python unwritten, there is nothing to compare here. Okay, so Julia is really a fast language, and here at least as fast as C. Okay, for this function, but it's true over different other problems. Let's come back to my slides. I want to also tell you that Julia is really easy to understand. So we already said that Julia is fast, but it's fast in solving or computing. But Julia is also fast in learning. Okay, the language is very intuitive and easy, and everything you think should be written in that direction, it's written in that direction. Okay, and also Julia is really easier and cleaner than C++. And you can avoid the two language problem. Okay, two language, one for rapid prototyping and one for speed. Here you have both in one language. And especially if you are like me with many responsibilities, you are very happy if you are available for 30 minutes in your day. And you can do something in 30 minutes in Julia, probably not so much in C++. So this is one of the reasons I like this language. I can still practice somehow. So let's explore some data frames, array, vectors, function, and broadcast, and to see how it's easy to use Julia here. So I'm coming back to my REPL here. I would like to use different packages. So we talk about the DataFrame and the CSV language. Okay, so then I'm using these two packages. I would like to load one file, so I'm going to use my shell here to show you that I have this big file, city temperature here. Size is 135 megabytes, so that's a big file. I get it from Kaggle, and this is a list of different temperature, different years, different months, different city around the world. Okay, so that's a big file, and we're going to put this file into DataFrame. I'm also going to use the macro time just to show you how fast is this loading, okay? So then I am using the syntax DataFrame, and then I'm loading the file. So that's the syntax here. You see that we have the completion here, so that's very interesting. So this is a big file, and this is loaded. It is loaded here into a data frame. A data frame is let's say structures. So it was fast. We have seen here 8 seconds for reading this big file. And this is a large one, okay? So we have 2.9 million of different lines. But once it's loaded, then you have access to values here very easily. So you see, you can get the element of one column, which is the average temperature column, and very easy to use. I want to make some statistics here. So I just call again the package statistics, and I can calculate the mean of the temperature. Okay, so that's the mean of temperature. So the mean of temperature is 56 degrees. Yeah. The files are coming from the some US guy. So temperature is given in Fahrenheit degrees. Let's just make a function to convert it to Celsius. So I just declare my function to Celsius of x. I don't use types for this, but I can just make precise types if I want. But Julia is going to do it for me. And then so the calculation, if you remember it, is x minus 32 times 5/9. I convert this. And then now I have my function that I can call here. So I can call my function over the data I want to see here. Okay, so you see that it's very easy to manipulate. Let's save this DataFrame vector into something called temperature, so it will be easier to practice. Something else I want to show you is that there is another way to make there is another way to make functions. So I just use this 2c function of x equals and just put the same calculation here. So you see that I've made this function on the fly, and of course the result of okay, I missed the C here. The result of this function is the same as before. So I like this ability of Julia to write quick functions when you need it immediately. Okay, so that's very impressive. So we have this vector here, temperature. You have all the values in Fahrenheit degrees, which is not very suitable for European people. So let's just decide to change this vector to another vector with degrees Celsius temperature. So it means that you need to apply your tuck function to every cell of this, and this is doable here with the broadcast. So I'm going to call this vector ctemp. And I'm going to broadcast, so this is a shortcut of the broadcast function, but broadcast the tuck function over all elements of the temperature vector. And it's done. So ctemp now is the same vector, but with the value in degree Celsius. And of course, you can call the mean function over it, and then you get the same value. So this is very nice here. Another feature that is very impressive here in this Julia language is the pipe function. So if you are a Linux user like me, and you probably do a lot of bash scripts and stuff like this, and this pipe allows you to chain different kind of commands. So I have this mean function, and I want to get the floor of it. So I just pipe with floor function. It's equivalent to write the floor of mean of ctemp. Okay, so that's of course the same, but the call of with the pipe is really easier to understand. So sometimes you have like a round function, so you want to round the value with 2 digits. So the call will be this one. So ctemp, okay, and digits equals 2. Okay, so that's a call, but it sounds sometimes more complicated than using the pipe function. So if we come back with the mean ctemp here, so sorry, you can just pipe here with round. The problem is that round has parameters, so you cannot really pipe like this. So you just make or create on the fly an anonymous function which associate x to round x digits equals 2, and then you get the results. So then this is another ability. And of course, if you are a fan of this grep or pipe or whatever, you will love this ability of chaining these calls of functions. I can show also another way of using this on-the-fly function. So here you want to count the number of times the temperature is greater or equal than 43. Okay, so that's you count these values over the vector ctemp, and then you see that you have 10 different values. So you can even create a vector with these 10 values by filtering your ctemp. So I'm just doing the same, greater than. Okay, you remember that we can use the Unicode values. So greater is \GE, like in LaTeX of ctemp, and then you get a vector v of these elements. Okay, so that's very very nice for us, and we can also round this value, let's say with 1 digit or 2 digits, or let's say 1 digit. Okay, so then I'm going to apply the round function and broadcast it to this. So round dot open parenthesis, and then I'm just round v with digits equals 2, and then I get this vector here. Okay. So, and what I can do also with this vector is that I need to use the stats by base package. And I can just make a sort of the count map, which is a very nice way of sort. What is sort? Okay, that's not very nice. Let's make the count map first of this round. Period v and digits equals 2, and then you obtain a dictionary telling you how different numbers you have in each category. So you have two numbers of size 43 of value 43.0, four numbers of value 43.28, and so on. So you see that you have a bunch of functions here ready to use for solving your problems. Okay, let's come back to the presentation. I already mentioned that there is a set of packages available here. So let's go to the presentation of the packages here. So you have this website, juliapackages.com, and you have here different packages. So if I'm not wrong, then there are like 9,000 different packages, and you have different categories here. So mathematics with graph theory, optimization with nonlinear or linear programming optimization. So you see all of this, and if you want to know more about the package, just click on it, and here you have the website and the GitHub of the package, and you have a description of the package, and sometimes just some small example here. Okay, so that's very nice here. Now let's explore some packages. So I'm going to code and show you this piece of code, very simple here. So you have like a bunch of packages for manipulating graphs. So graph plus, simple weighted graph, and the package delimited file just for reading a file. Here I create a graph and I just load the cocycles, and then I have this simple weighted graph with the values I get from my file. And then I can display the weights. And I'm going to call the Dijkstra algorithm here directly. So you see that you have this Dijkstra show the sparse function. And then I print the results. Okay, so I can just play here the source code. So you see that's my graph here. And then I just run the Dijkstra algorithm from node 1. And if you remember well your classes, then the results are the list of parents for the nodes and the distances from node 1 to this node. And then you can even draw the graph here. So that's very easy for teaching, for example. You don't have to bother with different packages or graph capabilities or drawing capabilities of yourself. You can just play this, and you have immediately the drawing ready for your class. And you can, of course, export here this drawing. Okay, so that's very nice. Another way of doing this is to see what we can do with the Plotly.js package. So you probably know this package because it's widely used in different PCs. So I'm going back to my repo. So here I can just paste the piece of code I just copied before. So this piece of code is very simple. I use the Plotly.js, and for all the data I have here, I just select 3 different years, 95, 2005, 2015. And then for the city of Paris, I just gather the temperature and calculate the average value for each month. Okay. And then I just want to plot these curves. So that's something really fantastic. The Plotly.js figure come here. And so you see what is inside this figure. What I like here is that you can have precise information on your data. You can also zoom on a part of your curves. And you can also come back here and just output the figure as a PNG file or even HTML if you want to use this information. And this is always, even if you export as HTML, then this is always interactive plotting. So that's very convenient for working here. Last thing I want to show you, and this is back into my notebook here. I have this notebook for showing you the capability of mathematical programming here. And this is a very classical one, the cutting stock example. So you want to cut table legs in master tubes. Okay, so you have 3 different sizes: small, medium, and large. And you have master tube of 2 meters. Small are 40 centimeters, medium are 60 centimeters, large are 70 centimeters. So one classical formulation for solving this problem is just to calculate or pre-calculate the patterns. So how are you going to cut the small tubes or table legs in the master tube? So you just enumerate all the different patterns, and then you just have a one variable or one set of variables saying how many times you are going to use this pattern, okay? And you want to minimize the waste, which is pre-calculated for each pattern. So that's very easy way of calculation. So I'm not going to show into details how you can generate the patterns, but it's an easy problem. So now we have the patterns. We can read the data here, and then here are the pattern. So then you see we have 23 different patterns. For each pattern you have the waste and then the composition. For example, this one is 5 small table eggs and the waste is 0. Okay. So you want to model the problem with this jump package. So you just declare a variable for your optimizer. Here I'm using the ICE optimizer. I declare the model, the cutting stock model here with my solver. And you see that I have the variables. So for this model, I have the x variables going from 1 to n. So that's a vector of variables and a positive integer. Okay. Constraints is only one set of constraints. So you have to satisfy the demand for each kind of demand. And you have to satisfy exactly. So you just count the number of time you cut the table legs in different format, and you ensure that it's exactly equal to the demand. And you minimize the total waste, which is pre-calculated here. So what I like and what my students like also is that this representation of the model is very close to the mathematical model. So you see that x is z plus in z plus, then it's really really close to that. And the demand function is sum of mij xi for I equals 1 to n. So this is that part equals dj. Okay, and then for all j is here. Okay. So you see that's very close to the mathematical model, and that's why I love it. So now we can solve it and calling the optimize function. So okay, I have to execute this one first. Okay, so that's the I solver here. So that's the output of the I solver. I'm checking the termination status just to be sure that I get the optimal results, and then I print the results. So the result says that I'm using 377 tubes with a total waste of only 120 centimeters. Okay, so that's my results. The pattern 5 is used 200 times, pattern 15 used 1 time, pattern 18 used 150 times, and so on. Okay. And what I like here also is that if you want to change the solver, so you just have to, as long as Gurubi is correctly installed on your place on your computer, then you just have to change two places. So using Gurubi and then set the Gurubi optimizer, and then you just play here. So you have the Gurubi optimizer running, and you check the termination status, it's still optimal, and then you check for the results. And so you see that the objective function is still 120 centimeters, so that's the same objective function, but the composition of the solution is a bit different. So this is what I like here. Another feature I forget to show you earlier is that when you are inside Julia, and let's go back to the REPL here. So when you are inside Julia, you can access to the package manager directly from Julia. So you press the closing square brackets and you enter here. And if you press status, you see that you have the list of packages that are already installed here. And you can add a new package by pressing add example, and then it's going to check. If the package is already installed, no change. If you want to remove a package, then just press example. You can add this package again. very easily, updating this package. And when it's done, just go back into the Julia repo, and you can use this package that you have just installed here. Okay, so here this is a dummy package for a demonstration, but it's already available for you. So that's very impressive, all this package environment and how you can use it. And as you have seen, then we have everything we need for solving problems here. So let's go back to the presentation. That's the end. That's almost the end of it. So what is the conclusion here? There are not only advantages of using Julia. First, Julia is a young language, started in 2012, if I'm not wrong, but it's still evolving, and sometimes you have like major changes in the syntax language, and then makes things difficult because you have to revamp your code. You may have problem with compile time sometimes, but not very often. And the ecosystem is sometimes immature. The reason is that some people, they develop some nice packages for their needs, but there is nobody to maintain these packages in the long run. So. But things are really improving, and you have also some subtle syntax tricks. Sometimes difficult to get, but could be an advantage. I mentioned already several times Julia is really easy to learn, and you have seen the pieces of code that I've shown you are really easy to understand. Julia is also very fast, we have shown that. And Julia Reaper is amazing, and if you are like me, a Linux user, then you will probably love it. But if not, then this is the same. We have also seen many ways to use Julia. So you can use your classical editor, you can use the notebooks, you can use the REPL and whatever. And you have the subtle syntax tricks that I love. Also, those very big advantage for me. My conclusion would be, if you learn Julia now, you are going to thank yourself in the future. So please, make the efforts, and it will take you a very short piece of time to learn Julia. Good luck, guys, and if you need my help, I would be happy to contribute.